Good morning. We've got a midterm coming up, midterm 4. We also have a final exam coming up right after that. So we are definitely getting ourselves prepared for both of those. But let's take a look at midterm 4 first. We've got some practice problems as we've had for the other midterms. So let's go ahead and take a look at some of these. So again, this is a set of problems that appeared on a midterm from several years back, and I've got two sets of these. So the midterm is going to be the same format that we've been working from. Let's go ahead and take a look at the practice set of problems that we've got here. So in the first problem, we are looking at the properties of quantum states of the electrons in atoms. So this is kind of a chapter 39 question. And what it's saying is this. If you remember back in that chapter, we looked at X-ray production. We said that as you move through the periodic table, the energies of these electron states just get deeper and deeper. There's larger and larger binding energies for these lower quantum states. So quantum states at the n equals 1 or the n equals 2 level become enormous. They have these really, really large binding energies. So if I've got a couple of electrons in the 1s state, and one of those electrons gets bumped out of the atom, then an electron from a higher state will drop down. So what we looked at were examples of what happens when an electron from level 2 drops in energy and fills that vacancy. And when we have an electron dropping from state 2 to state 1, how much energy would that photon have? And it's going to have thousands of eV. As we move through the periodic table, these energies just go up. And the other story we had talked about here is that it was actually these measurements of X-rays that finally established the complete periodic table. The periodic table had been put together. There were a few ambiguities because, as you guys know, if you've taken chemistry classes, when you get into the transition elements, for example, or the intertransition elements, chemical properties are subtle. And so it's not always straightforward about which order the elements are in. And we want to be able to place them in terms of the protons in the nucleus. So we just want to order the elements 1 through 118 or whatever. We just want to do it by proton number. And X-rays follow that pattern. So as you move through the periodic table, every time you add a proton, not just a general trend, but absolutely every time you add another proton, these states drop lower and the separation between them increases. So the n equals 1 level drops the most. The n equals 2 level doesn't drop as much because of shielding from the n equals 1 level. And so what we end up with is, to a good approximation, we can say that the energy of a photon created when an electron drops from state 2 to state 1 is equal to the energy of state 2 minus energy of state 1, where here's the good approximation. The energies of these states roughly being given by our old friend minus 13.6 eV times Z effective squared divided by n squared. Oh look, I remembered the n. I'm sorry, I remembered the square. Z effective is equal to Z minus 1. All right. So this is the approximation here, is that I can use a Z effective that's roughly Z minus 1. If I do that, then the familiar formula we've been working from gives us a good approximation. And this was used in experiments to help establish the ordering of the elements in a few locations in the periodic table, in a handful of locations. All right, so the elements that have been, that we're looking at here in the problem, it says let's look at copper, silver, and gold. Now if you guys have taken chemistry classes, or if you've stared at a periodic table, copper, silver, and gold, they're in the same column. Is that what they're called? It is column, right? Columns and rows. So they're in the same column. The Z value, the number of protons for copper is 29, number of protons in silver is 47, number of protons in gold is 79. Okay, so this, I thought this might be an interesting comparison to see how the energies of the X-rays being produced. So when this electron drops, the photon comes out, it's going to have a lot of energy. So for copper, using the Z effective formula, the Z effective approximation, copper Z is equal to 29, Z effective is 28. That says that the n equals 1 level is given by minus 10,660 eV. The n equals 2 level is at minus 2,666. All right. The difference in those two energies gives us a photon of about 8,000 eV. Now I've written this as 7,996 eV. And when I did HC over E to get the wavelength, I converted into picometers. This came in at 155 picometers. Now, what's going to happen if we go from copper to silver, which has an atomic number of 46? It's got 46 protons in the nucleus. Well, for a neutral atom of silver, the E1 energy level is at minus 28,700. Look how that climbed. So that went up by, well, we went from 28 to 46. That's not doubling. But when we square that effect, this more than doubled the energies of these. So these are much deeper now. And the difference between them has gone from 8,000 to 21.6 thousand eV. So from 8.0 keV to 21.6, and then continuing on to gold, the Z effective here would be 79 minus 1 gives us 78, and calculating the energies of electrons at quantum state n equals 1 versus quantum state n equals 2, that gives us a difference of 62 keV. So we went from 8 keV to 22 keV to 62 keV. The wavelengths have dropped from 155 to 57 to 20 picometers. Okay, so again, it's using the formulas that we developed for the creation of X-rays, specifically from n equals 2 to n equals 1. And we looked at, and this is a formula we use to estimate these energies throughout the periodic table. All right, questions on that? Okay, so this is from chapter 39, and any questions, stop by office hours. Let's move on. Take a look at the next question here. So the next question is looking at nuclear physics, and it's looking at the decays of radioactive potassium. So naturally occurring potassium is the 39 isotope. So potassium 39 is by a large measure, by a lot, pretty much all of the potassium in nature is the 39 isotope. But there is a small amount of potassium 40. What's that doing there? Well, it has a really long lifetime. And so what happened is when potassium was being formed by inside high mass stars, when really, really high mass stars were running nuclear fusion processes and potassium was being formed, a little bit of potassium 40 got generated along there. And then, the stars supernovaed, and that material was scattered out into space as little bits of what we call dust. I like that. So when the supernovas detonate, the little specks that are left over are called dust. And within that dust, Some of that has potassium in it, and some of those potassiums are potassium-40. Now, currently, on planet Earth, of every 8,500 potassium nuclei, only one of those is radioactive. Now, I think I mentioned in class that when my kids were in elementary school, as they went through, I think it was the second grade, each one of them would come home and say, hey, we're not supposed to be eating any bananas because bananas have potassium and potassium's radioactive. And I go, okay, there's really no avoiding potassium. Potassium biologically is pretty essential. We just have to deal with it. Our DNA has enzymes running back and forth, checking to see if there are any simple errors that might have occurred. The potassium-40 could damage the DNA, for example. But that's kind of the best we do. That's what nature has come up with. That's what has developed over these billions of years. And we're not going to stop eating bananas because it's a good source of potassium and we need the potassium. There's no simple way to eliminate the potassium-40 that we're going to ingest along with those. Anyway, so getting back to the problem at hand here, the potassium has a half-life of 1.28 billion years, so it's still around. It can decay. It's got a lot of decay modes. It can decay by beta minus, beta plus, or beta neutral. All of those are allowed decays for the potassium-40. A 50 kilogram person typically contains about, I was surprised it was this low. I looked this up. I was thinking it would be quite a bit higher, but a person's mostly water. Non-water stuff is probably only, 5 or 6 kilograms, but still, I guess there's a lot of carbon and oxygen and nitrogen and hydrogen. Anyway, we're going to take this 150 grams of potassium and ask, this 150 grams of potassium in a person, what would be the activity due to the potassium-40 within that potassium? So the 150 grams is not totally radioactive. It's only 1 out of every 8,500. All right. So to find out the rate at which these potassium-40s are decaying inside this person, we can take the number and divide through by the lifetime. Now, the half-life, we're told, is 1.28, 10 to the 9th years. That means that the lifetime is going to be the half-life divided by the ln of 2. And that means that the lifetime for potassium-40 is 1.85 billion years, and that converts over into 5.83 10 to the 16 seconds. So I'm going to say practice your conversions between years and seconds, because it's going to come up in some of these problems. You've seen this in the homework, in the examples in class, so these examples are going to come up. So this is the lifetime. So I got the tau calculated. Now, how do we calculate in 150 grams of potassium from this person, how many potassium-40s would there be? Well, I can take this 39 grams, which is the molar mass, 39.0 grams of potassium is Avogadro's number of potassiums, and then out of a total of every 8,500 potassiums, one of those is going to be potassium-40. So, doing all those calculations, I ended up with, in this 50 kilogram person, there are 2.7 10 to the 20th radioactive potassium-40 nuclei. I don't know how you guys feel, but that sounds like a lot to me. But it's much less than a mole, right? It's not even a thousandth of a mole. So let's see how much at risk we might be. Well, the decay rate then would come from taking that number of potassium-40s and dividing through by the lifetime, which is in seconds. Ooh, look at that. Our 50 kilogram person has 4,700, roughly, 4,700 decays every second. 4,700 decays every second from potassium-40. Okay, that sounds like a significant number of decays. I know that, atoms are really tiny, and so that represents, how many, trillions of cells do you have? And so, several thousand a second, no big deal, right? Let's take a look and see. So in part B, they said potassium-40 decays with an energy of about 1.4 MeV. So let's take that decay rate and let's multiply by the number of seconds in a year. And then I put in 1.4 MeV per decay. And so what units do we have now? Well, we have MeV per year. What we're after here is energy. We want to find out, specifically, what are they saying? And specifically they are saying, what's the annual dose? So they want to figure out what the dose is. And so doses are in terms of energy per mass of whatever is experiencing, whatever is being exposed to the radioactivity. Now in this example, it's the entire person that's being exposed, right? You're going to have potassium as an electrolyte in all of your fluids, everywhere. So potassium's going to be there. And so this is total exposure throughout the person. So we get to divide through by the total mass of the person. Now, when I calculated the total energy of all the decays for an entire year, it worked out to be 0.033 joules. So apparently, even with 4,700 decays happening every second, it's just a fraction of 1 joule that we're being exposed to. And that joule is spread out in this person over 50 kilograms. So the dose that they're getting is 600 microgray. So a gray would be 1 joule per kilogram. Now, it wanted this in centigrade, which is more commonly used, I think, by doctors and such. Radiologists and whatever are going to be thinking in terms of centigrade. So I converted this, it worked out to be 0.0660 centigrade. Now, in part C, it says compare this to the total background. Background exposure to radiation, I looked up and it stated this as, that's a pretty small number too. So the background exposure for an entire year is expected to be about 1/3 of a centigrade. And what we have here is about, 1/6 of that. So this decay of potassium-40 is responsible for maybe 1/6 of the radiation that we're exposed to during the year. So it's an important part of that background exposure. Now, there's a couple things I was a little skeptical about here that I should point out. I would have to go back and remind myself where I got this 1.4 MeV number. I didn't do that. I should have done that. Find out if this is really the Q value. And then, the good news here is that when we look at these beta decays, let's take a look at them because that's part D. So here is the beta minus process, beta plus, beta neutral. In the beta minus process, one of the neutrons converts to a proton. That means element 19 becomes element 20. The mass stays the same, roughly. So the mass number does stay the same. And that means that potassium-40 would be decaying to calcium-40, which is very stable, if it undergoes beta minus. Now in this case, the Q value is going to be less because it's producing we have to take into account the extra electrons that are, no, I've got that backwards. So this one, the Q value is going to be a little higher. Okay, so, but notice that the neutrino, there's an anti-neutrino, and the anti-neutrino is probably going to carry away half the energy. we're not going to be exposed to that because it's very, very, very unlikely that a neutrino would react with anything within us. And so the neutrino energy is pretty much carried away safely. And so maybe only half of the energy that we calculate are we being exposed to. Now in the beta plus example, the proton turns into a neutron. That means the electron coming out is not an electron, but an anti-electron. So it's an E plus. This also produces a neutrino. And again, we're expecting that the neutrino is going to carry away maybe half the energy. On the other hand, the E plus is going to react with one of your indigenous electrons. And so that's a problem. The E plus and E minus are going to decay into high energy photons. You're going to be exposed to that. So again, I feel like this is a whole separate problem, but you could do a Q value on each of these and then include here the E plus converting, the E plus, E minus converting into some photons, because the Q values are going to be different. This 1.4, I don't know if that's an average value. I'd have to go back and take another look at how frequently these three different decay modes occur. I don't think it's 1/3 each. Some of these are probably favored. Now there's a third decay mode, that's electron capture, and I've been calling that beta neutral. Now this one's really good. I'm hoping everything decays this way, because in this, the proton is turning into a neutron, but instead of generating an anti-electron, it actually takes one of the existing indigenous electrons and that converts into a neutrino. So in this, it's just the neutrino coming out. Nobody's afraid of the neutrino. That's not going to cause any damage. And so the only thing coming out, you know, there's an argon that could be coming out with a fair amount of kinetic energy. But very likely that beta neutral would, the Q value that would actually, the ionizing radiation effect would probably be really low. So anyway, those are the three decay modes that we're looking at for that example. Questions on any of that? These radioactive decay problems are interesting, huh? I think they're pretty interesting to look at. Here's another problem, problem 3. This is looking at a nuclear power plant using uranium. So this is an example of nuclear fission. And so if we're going to have a power plant, a nuclear power plant, based on fission, how much uranium is that going to require? So it says this, it says the plant produces 6,000 megawatts of electric power. So remember, watts, that's a rate at which energy is being generated. So they want to know during a year how much energy would be produced. And so we can take the 6,000 megawatts, now this is electrical energy, 6,000 million joules every second, and then that happens, oh, it's for the day, it's not for a year. Read carefully. Okay, always read carefully. So this is just one day. One day is 86,400 seconds. So it says each day of operation, it is producing 5.18, 10 to the 14th joules. Okay, that's how much energy is being produced each day. I had to take the power and multiply by a time to get a certain amount of energy. Now, part B is asking how much uranium-235 would be consumed during each day. Now for this, I've got to figure out how to use that efficiency. So the way I worked that in is this. I started out, here is the amount of electricity being produced each day. That's the electric energy being produced. For every 40 joules of electric energy produced, I am going to need to generate 100 joules of thermal energy. Now this is maybe one of the most common errors that gets made in these type of problems, is by getting the efficiency backwards. So I can't use 40 joules of thermal energy to generate 100 joules of electricity. it's the 100 joules of thermal energy I need in order to generate just 40 joules of electricity. This takes us back to physics 3A when we were looking at heat engines, taking thermal energy and converting it into mechanical energy. These generators are spinning, these electric generators are mechanical in nature, and so what's happening is 60 joules are going right off into the environment as thermal energy when we run these fission reactors. Okay, so I got my efficiencies taken care of right there. And then what I can do is just do some units conversions. I can take the joules, convert them to MeV, and then in the problem, what they tell us is one fission releases about 200 MeV of thermal energy. So one fission requires one uranium-235 nucleus. That's all, just one uranium-235. And so that nucleus is going to be part of an atom, and the atom is going to have a mass of 235 grams per mole. This is a mole here. And running through this, let's see what happened here. Joules of electricity canceled joules of electricity. Thermal joules, this is thermal joules. The MeV canceled MeV. The numbers of uranium canceled numbers of uranium. I am left with, what I ended up with was 15.8 kilograms. That's not that much. 15.8 kilograms per day. Now this is a major power plant, 6,000 megawatts, and I only need 16 kilograms of uranium. So that's not much. That's a pretty small chunk of uranium that we would need to operate this for one day. Now in part C, they say actually in a power plant, we never would need to enrich the uranium-235 so that it's 100% pure. In fact, that would be dangerous. We could possibly set off a fission detonation of some sort if we enrich the uranium-235 too much. And so what we do is the uranium that goes in has been enriched, so about 3% is uranium-235, 97% uranium-238, and it's not concentrated. It needs to be spread out through a fuel rod, a fuel canister that gets inserted into the reactor so that if neutrons are present, they don't set off a nuclear fission reaction. We don't want that to happen until the uranium is inside the power plant. So if it's 3% uranium-235, 97% uranium-238, what mass of uranium would be needed for one day and how much would be needed for the year? Now to do this, oh look, I did two part C's on this. The first thing I did is I did a molar mass. If I take a combination of the 238 isotope, 97%, and a 3% of uranium-235, I ended up with a molar mass that was 230. Did I end up using this? I don't know that I did. I did. Oh, I didn't. Okay, I'm going to cross this out. So I'm going to cross this calculation out. I mean, I left it in to see how I would do a molar mass. I ended up not using it. Maybe I should just leave it in. But what I did instead was this. I took the 15,800 grams of uranium-235, and I said, how many moles would that be? And then this is going to give me the number of moles of uranium-235. And then I said the number of uranium-235. For every 3 uranium-235s, I'm going to have 97 uranium-238s. And then I undid the number and converted that back into grams. What it said is that if I have a 97% to 3% mixture, then for every 15.8 kilograms of uranium-235, that would be accompanied by 517 517 kilograms of uranium-238. Does that make sense? Boy, I hope so. 3%, yeah, that seems about right. So this is about 3% of that mass. So yeah, so each day we would actually be putting in, we would be using, you know, half a ton of uranium for the power plant. And so, and that's each day. So if I scale that up for the whole year, the total amount of uranium would be 533, and that would include the 235 and the 238. And so the total amount of uranium I'm bringing into the power plant each year would be somewhere around 200,000 kilograms, or 200 tons. Now, 200 tons might sound like a lot. Uranium's very dense. So the 200 tons might not be such an enormous amount in terms of volume. And then the other issue we should bring up is, let's consider other power plants. If it was a natural gas power plant or a coal power plant, how much coal would be sent through that power plant every day? And you'd have train cars loading up with coal in order to keep the power plant going. So anyway, these are the numbers that came out. Trying to decide if I want to leave that in. That's not a bad calculation, just as an example. But this is, I kind of changed my mind halfway through as to how I was going to solve the problem. So I solved for the amount of uranium-238 first, and then added that on to the uranium-235. Okay, maybe I'll leave it in. Let's take a look at this last problem. We're headed like we need a break here. So for the last problem, it's saying, where did all the carbon come from? If we go back, you know, billions of years, has the amount of carbon in the universe remained fixed, or is the universe somehow creating more and more carbon as time goes by? Now in chapter 44, what we learned is that the nucleosynthesis, the creation of nuclei heavier than, well, the creation of any nuclei, other than just simple protons, requires kind of extreme conditions of temperature and pressure. And the only two times, well, the only three times maybe, that we expect heavy elements like carbon were formed, could be formed, was either in the original high temperature, high density plasma state that we call the Big Bang. Now it turns out that we don't think much carbon was generated at that time. A lot of helium formed, a lot of helium-4, but not much carbon. Now where we do think most of the carbon-14 came from is nuclear fusion in high mass stars according to this fusion reaction right there. So it's a little difficult to generate carbon because the material you're starting from is helium-4. It turns out there are not really any especially stable isotopes of beryllium or boron. You can generate those, but it's hard to get a complete series of steps leading to carbon. It's actually more likely that the carbon fusion reactions were from three heliums coming together within a short enough time interval that it didn't fall apart. So three helium-4s coming together to form a carbon. Now the Q value, which is what they start off with here, for this reaction, there's a bunch of high-energy photons coming out too, would be taking the mass of the three heliums, subtracting off the mass of the carbon. That gives us a mass of 0.007809 each time that reaction occurs. Now that's in atomic mass units. If we convert that into MeV using our conversion of 931.5, that gives us 7.274 MeV. So that's the amount of energy released every time this reaction occurs. Now in part B, what they're asking about is, let's imagine a star that starts out as 100% helium. So I should point out, we don't think this ever happens, to where the entire star becomes helium. helium is going to be formed, well, I guess the low mass stars could do this. So the low mass stars run fusion reactions more carefully, more slowly, and it provides enough time that most of the hydrogen can cycle through the core, and so helium can be formed. But in the high mass stars are messy eaters. So once the helium gets formed in the core, then the star is moving on to carbon fusion. And the stars probably don't survive long enough to have all of the helium cycle through the core. So in any case, let's just say this. So we're imagining an entire star made of helium-4. For that star, what fraction of the mass will be converted to kinetic energy? And in class, what we've done is we've taken the Q values, divided through by the mass that we've invested. Now, the mass we've invested in this are the 3 helium-4s. So those are the masses that we have invested in this process. And so if I take the Q value that we're getting, now I rewrote this in terms of atomic mass units, because I want these to cancel out. So I'm going to put in how much missing mass is there compared with the mass that we put in. And this worked out to be about 1 part in 1,538. So let's take the total mass of the star and then take 1 kilogram of energy being produced for every 1,538 kilograms of helium-4. That means that 3.25 times 10 to the 27 kilograms of mass has been converted to energy. The total mass was 5 times 10 to the 30th. 3 times 10 to the 27 is being converted to energy. So it's that fraction. It's less than 1 part in 1,000. But when we plug that into mc squared, that works out to be 2.9 times 10 to the 44 joules. So that's a lot of energy that's available to this star. Imagining that it's going to run this process where it generates a lot of carbon. Now the time that the star could continue running this reaction depends on how much energy is available, which we just calculated, and then you have to divide that through by the rate of energy being used. In the problem, they tell us that the power output of this star, I hope I got this right, is 2 times 10 to the 27 joules per second. So I've got this amount of energy available, and the star is running through this reaction and producing 2 times 10 to the 27 joules per second. That gives me a time of 1.46 10 to the 17th seconds. That's a lot of seconds that we're looking at here. So if I take the 10 to the 16th seconds and divide that through by this 31.56, that's a decimal right there. 31.56, 10 to the 6 seconds per year. Did I mention there's a decimal right there? Don't lose track of it. Otherwise, you'll stop by office hours if you have any questions with any of these. I should go back and make that more visible. And this worked out to be 4.64 billion years. So this star, if it's using helium to carbon fusion, and it was entirely helium-4 to start with, that would be enough so that it could survive, it could shine, maintain its brightness for 4.5 billion years. That's a good long time. Questions on any of that? All right, so let's do this. Let's take a break, and then we will come back and take a look at that next set of problems. Any questions? Stop by.